program. Yeah. Let me give some words about Professor Stefan Kycia. He's professor and chairman of the physics department at the University of Guelph. Yes, Guelph is correct.
Guelph.
Guelph. Situated in southern Ontario, Canada. Is the English part? Yes.
Yeah,
I think yes.
Yeah,
English
that's
part.
right.
Yes, yes. He's also a principal investigator and team leader of the Brockhouse X-Ray Diffraction and Scattering Sector at the Canadian Light Source in Saskatchewan. Yes, Saskatchewan is in the center of Canada. Yes, and also Professor Kycia research is dedicated to development of new X-ray diffraction methods. And before working at the University of Guelph, Professor Kycia worked as a research staff at Laboratório Nacional de Luz Synchrotron. Then if people want to ask in the end questions in Portuguese, they can. Yes, I think that you still remember Portuguese.
Yeah.
Okay, good. Yes, yes. So far. And before that, he was working as a staff scientist at Cornell High Energy Synchrotron Source, CHESS, in US. Yeah. And now Professor Kycia is currently the president of Canadian Institute of Synchrotron Radiation and is contributing to the progressing synchrotron science in Canada. Then thanks again, Stefan, and now I give the time for your presentation.
Yeah, okay, yeah. So thank you very much, Fabiano. And it's really nice that you invited me. Yeah, it's been some years since we last communicated. And yeah, I'm very glad to be able to share what's happening here in Canada, and just introduce myself and the research we've been doing. So Fabiano said that many of you are students, and so and maybe not even not necessarily experts in X-ray diffraction. So my goal is going to be to well, make this as useful as possible. Okay, so teach you some major, the fundamental important aspects of what makes the research I do and my group work. Okay, so let me see. Yeah, so como antes de falar de ciência, eu vou apresentar um pouquinho a história, ok? E essa parte eu posso falar em português, se você quer. Então, agora eu moro em Canadá, mas antes eu trabalhava no Synchrotron, lá em Campinas, junto com o Fabiano. E depois, chegando aqui, foi 2004 que eu montei uma proposta grande para construir uma linha de raio-x aqui em Canadá, e nós conseguimos. E eu acho que tudo foi isso, deu certo por causa dessa experiência que eu ganhei, em grande parte foi a experiência que eu ganhei trabalhando lá no Synchrotron brasileiro, Laboratório do Synchrotron, Laboratório Nacional de Luz Synchrotron, lá em Campinas. Aqui uma foto eu coloquei essa aqui antes de mudar para Campinas, foi mais ou menos 1999 que eu mudei para Campinas, mas antes eu estava trabalhando no Synchrotron. Eu não sei, Fabiano, você está vendo o meu pointer ou não?
Sim, sim.
Ok, bom. Então, esse aqui é uma foto do campo de futebol, e é futebol normal, sabe? Não americano. Isso é importante. Futebol, e embaixo desse campo é um synchrotron. E esse synchrotron ainda funciona. Temos foto aqui no lado esquerdo. Esse aqui é Hans Bethe, andando de bicicleta pelo anel no começo. Então, esse aqui foi montado em 1965. Mas essa foto aqui no meio, esse é muito antigo. Esse synchrotron não foi desenhado para trabalhar com raio-x. Esse mais era para colisões particular, ok? Eu acho que particular, não sei, entre elétrons e positrons, hein? E esse acelerador foi feito para isso, para high energy physics, hein? Mas o que aconteceu os cientistas fizeram uma calculação acho que foi Schwinger que fez essa calculação, e calculou que o luz ia espalhar. Cada vez um elétron faz uma curva, por causa de uma imã, ok? Vai espalhar luz. E ele fez uma calculação que por causa da energia desses elétrons fazendo esse círculo, eles são relativistas, hein? Bem rápido. E eles vão espalhar, construir raio-x, ok? Então, com essa informação, alguém pensou, ei, minuto, esses físicos estão fazendo medidas, ok, de high energy physics, vamos tentar para usar esse raio-x no mesmo tempo. E então, o synchrotron lá em Canadá, não, Cornell, foi um dos primeiros que foi usado por raio-x, ok? Mas, no mesmo tempo, os particle physicists estavam fazendo as medidas deles e nós estamos aqui, uma foto, aqui lado direito, essa aqui foi eu, ok? Em 1999, trabalhando em um laboratório no subterra, e eles chamaram nós, eu não sei como traduzir em português, mas se chama parasites, ou parasitic users, porque eles não gostaram de nós. Nós entramos nesse laboratório para usar o raio-x, ok? E foi muita intensidade, deixou nós fazer medidas que era impossível, completamente impossível, dentro de um laboratório normal, ok? Se chama House Lab, ok? Ok, vamos continuar. Aqui uma foto do synchrotron brasileiro em 1999, 2000, quando eu mudei para lá, e onde nós trabalhamos, ok? Mas esse synchrotron foi desenhado para raio-x, ok? Então, em verdade, em vários jeitos, era a melhor fonte para esse tipo de medidas. Aqui uma foto do primeiro synchrotron, e essa aqui é a linha onde nós trabalhamos, e eu ajudei para desenhar e montar essa linha e duas outras. Agora, ok, eu vou mudar para inglês, porque começa a vocabulário mais complicado. 1, 2, 3, ok. Mas se vocês têm perguntas em inglês, português, não tem problema. The difference between, a modern synchrotron and an older synchrotron, there are 4 generations of synchrotrons now. So I used to work at the first generation synchrotron, and the first generation synchrotron was designed for particle physics, but used for X-ray use at the same time. It means that the synchrotron wasn't optimized for X-ray use, okay? The second generation machines, there were a handful that were, many were built, and those were accelerators that were designed specifically for X-rays. But they didn't have all of the current technology. So this design on the left is sort of, what's that? Like a top view of the path of a vacuum chamber that the electrons might go through, and you've got different types of magnets, and they're like focusing magnets and bend magnets. See, what happens is the electron beam wants to separate. It wants to get away from electrons. Don't want to be next to electrons, right? And so you have to constantly keep on refocusing them as they spread out. You have to refocus them. They spread out. You have to refocus them, and at the same time, you're bending them into a polygon shape. And the first synchrotrons had patterns like this, okay, of bend magnets and focusing magnets. What the second generation machines had was they designed straight sections. Let's see if I can draw a little picture here. So in a straight section, I'll use this. What would happen is you would have, okay, there would be this region where the electrons just go straight, okay? And then what they would do is they would add magnets that would cause the electrons to do a slalom, like a sine wave. And what happens is, this is the important rule, is that accelerating charges radiate. So what happens is these X-rays come out right where you have the maximum acceleration, and actually here too. Okay. Okay. They come out and it all adds up. So if you can have like 100 oscillations in these straight sections, you're gonna have 100 times the intensity of just one bend magnet. And so the second generation machines had this capability, and that made them much more intense. Now, there's something called a wiggler. I'm going to just call it W. And then there's something called an undulator. I'm not going to, okay, I will spell out the whole thing. And those are two very different, two different types of, okay, what they call insertion devices. And they can put them in these straight sections and they create different spectra of X-rays, okay? And wigglers, they just, the X-rays from each wiggle just adds. While in an undulator, you actually have a coherent increase of intensity. So, well, if you had 10 wiggles, you would have 10 times your intensity. But if it was an undulator, you would have 10 times 10, okay, it would be 100 times the intensity. So that's something that second generation machines didn't have. They weren't designed for this. Third generation machines were designed with straight sections, okay, to take advantage of these insertion devices. Okay, so first was designed for particle physics. Second was designed for using bend magnets to create X-rays. And at each bend magnet, you could create a beamline and an experiment. And, you know, you could have like 50 experiments coming out of one machine. But the new machines, the third ones, were designed for insertion devices. And now what you have is something called the fourth generation. And I'm telling you about this because, well, it's not a very long story, but it's an important one. In the fourth generation machines, they're using a magnet arrangement like this on the right, where someone figured out that, and actually the Brazilian accelerator physicists were part of all of this, figured out that a much more complicated arrangement of magnets that more resembles, let's say, a circular path as opposed to a highly polygonal path, okay, produces a better beam, okay? The way I look at it is that if you think about it, the electrons going around the synchrotron, let's just say they look sort of like the Saturn's rings, okay? So it's not a perfect circle. It's sort of elongated radially, okay? And these electrons are going around and around. And what I'm getting at is that if this synchrotron has all the other electrons going around like this, the one on the right, the new one, has one path, okay? It's a much tighter circle. Now, the radius isn't smaller. The thickness of the ring is the thickness of the path there's more defined, okay? And so it's not like Saturn's rings. It's more like one circular path. And why is that good? It means that the source is smaller. The X-ray source is smaller. So the Brazilian synchrotron now in Campinas is made of this new design, and it's a much better machine, and it's revolutionizing the possibilities in synchrotron science. So here's a picture of the new machine back when before it was built. That's the picture I had, and I would show everybody here. Brazil is ahead of Canada. We have one machine. Our machine is more advanced than the first Brazilian machine, but it's far behind the new Brazilian machine. Okay, we're hoping to come up with a plan to improve our synchrotron and catch up to Brazil. Okay, here's a nice picture of the Canadian light source, and on a nice summer day, and it's a small machine. It was a little bigger than the original Brazilian one. Had twice the energy of electrons, so that was very good for synchrotron science. But it's far from equal to the new machine that Brazil has. Here's what the Canadian light source looks like inside. So you see it's just absolutely full of equipment. And what you see is that this is I don't know if you could see the picture, the circle, the electrons go in a circle, and then you have beam lines radiating out, okay, tangent to the electron path. So back in it was 2005 that I wrote this proposal to expand the Canadian light source. And so here's the design eventually of the sector that we built. And it's a material science, X-ray diffraction and scattering sector. And starting here on the left, okay, here you see a little bit of the ring, the bottom left corner, and then the X-rays come out straight. And what we've created is 3 beam lines. And here's what 1, 2, and 3 stations. And they're all complementary, and they have a very, very intense X-rays, and they can work simultaneously. So this one here is called the high energy, and this is the one that I'm going to mostly be talking about. Okay, here's an undulator, okay, beam line, and it's a lower energy, but it's a very intense parallel monochromatic X-ray beam. And this one here is more for small angle scattering, and well, we've got an interesting apparatus in there. It's a robot, and it was actually put together by IBM, you know, the company IBM in New York. I actually managed to get them involved, and they gave us like $4 million to produce a robot, and we put it together, and so they can do experiments from their, well, I guess their living room and their home, and in New York, while their samples are in Canada. Okay, and it's a fantastic apparatus, and during the pandemic they used it every day. It was amazing, like nothing stopped them. So so we've got lots of different types of uses. Let's keep on going. So yeah, this is the layout of the synchrotron, where the electrons go around in a circle, and this is our beam line, and there are other beam lines in the ring. We had to build the building out. Okay, see, this was the original building, was just like this. We had to expand the building, okay, to be able to create our beam line. So here's some pictures of the different types of equipment we have. It's all functioning now. Okay, we had our first X-rays at this sector in something like 2019. Okay, so it took a long time for us to build this sector. Okay. Oh, change subjects. Okay, change subjects. So here are synchrotrons around the world. So they're synchrotrons. This is a plot that actually I got from Ricardo Rodriguez, that I've sort of modified, and he was the top accelerator physicist in Canada, in Brazil, I mean, and I believe he was from your university. So here's a picture of all of these different synchrotrons, and it's a plot of what's called the emittance versus the circumference. And the emittance is just a measure of the quality of the beam, meaning how small it is and how parallel it is, okay, of the machine itself, the electrons. And what's happening is all of these countries are modifying, they're souping up, they're improving their machines to go to this new 4th generation design that the Brazilian synchrotron already has. The Canadian one is up here. So, the biggest machines and the lowest emittance is the best thing to have, okay? And unfortunately, Canada's over here. Whoops. So something we have to work on. But as a good scientist, you always, you have to always think about how you're going to use the equipment you have as best as you can. You don't have to have, just because supercomputers came out doesn't mean that you have to do all your computation on a supercomputer, right? Let's move on. I don't want to go too slow here. So diffraction. Here's the diffraction pattern that I took back in at the Brazilian synchrotron, and it's a very nice pattern. So if you think about X-ray diffraction, you think of Bragg's law, right? Oh, I don't know why that happens. 2d the sine theta. I'm writing with my finger, not my pen, so it's not good. Okay, lambda is equal to 2d sine theta. Every single set of planes in a crystal is going to create a Bragg peak. These Bragg peaks are very, very sharp, okay? And so you can measure their angle very carefully. And if you know the wavelength and you measure the angle carefully, you can figure out the d-spacing, the spacing between the planes. And the intensity of the peaks, tells you where the atoms are in these building blocks, the unit cell. So this is yttrium oxide. It's a very nice sample. And it was really measured to be able to show that the apparatus worked really well, and it did. And you could see in the inset a difference between the calculation and the measurement. And the difference is this tiny little glitch there. So what I'm getting at here is that a calculated diffraction pattern from a model, okay, is going to match the X-ray data really well, and vice versa. So it means that the X-ray data is going to really tell you in a reliable way the structure of your sample. Okay, let's keep on going. So the problem, and this is what I want to show you, is that yttrium oxide is this is a classic way of doing X-ray diffraction. You crush up a sample, it'll be like table salt, okay? And you put that in the beam, and you're going to get a nice diffraction pattern like this, let's say, okay? You don't need a lot of sample, very little. What's causing the sharp peaks, okay, is the long-range crystallographic order in these grains, these crystalline grains. Now, when we looked at nanoparticles, okay, this is Daniela Janset's samples of gold nanoparticles. And on the right, you see what happens as the nanoparticles get smaller, that first Bragg peak just gets broader and broader and broader. It's terrible. And the whole diffraction pattern looks ruined, okay? So the 2 nanometer particles are this worse curve like this. You can't measure Bragg peaks. The peaks are all overlapped. So one of the most important things I want to tell you about, teach you about in this presentation is how we're going to get around, okay, the problem, okay, this problem. So at the time, people thought, well, you're not going to use X-ray diffraction to solve the structure of nanoparticles. You can't use it because the particle sizes are so small that you don't get good sharp diffraction. You need long-range order to get sharp peaks. The thing is that that's not true. X-ray diffraction can get you information, and excellent information, about even nanoparticles and even amorphous materials, okay? So now you're going to draw a little picture. Now pay attention to this, because this is a lot of people, even people who've been working with X-rays for a long time, okay, don't get this, don't realize the difference, okay? When let's say this is a meter stick. If you wanted to figure out, let's say, well, if a meter stick was proper, okay, you wanted to find out whether that 1 millimeter was really 1,000 microns. You can't measure that 1 millimeter tick down at the bottom there so well, especially since the line is thick, right? This is an example. So what are you going to do? Is you're going to measure the whole length. You measure the whole length and you divide by 1,000, okay? And you figure out that a millimeter is 1,000th of your meter, don't you? I mean, but you're making an assumption. The assumption you're making is that there are 1,000 little ticks, that there are 1,000 millimeters, okay? And let's say there's no mistake about that. There are 1,000 ticks. But there's another assumption you're making. The assumption you're making is that every one of these ticks is equally spaced. That's the subtlety I want to tell you about. So what would happen if this meter stick was done in such a way that we had the lengths, the spacing between them was variable? That sometimes they were big spaced and then sometimes they got close. You would only be figuring out the average. You might come up with the answer being a millimeter still, because if the 2 millimeter sticks were 1 meter long, you would not know that 1 meter stick had equally spaced ticks and the other one didn't, okay? So this is something that this diffraction pattern is not sensitive to. It doesn't realize that you're making this assumption that all of the building blocks are identical, okay? It's giving you a sharp peak because it's like you're measuring the length of the unit of the crystallite, which could be a micron. That's what's giving you the sharpness, okay? But what's giving you the atomic distances, the d-spacing, is this trick I'm telling you about, okay? So the way you have to analyze data, if you're looking at something, oh, and by the way, what I'm getting at is that if you have a nanoparticle, your sample may only be this short, small. It's not a meter long. It's 10 millimeters long, okay? So the trick, even if it does work, it doesn't work very well, okay? This is the analogy to the problem, okay? Once you understand that, you'll understand why we're going to be analyzing the data we do the way we do. We have an apparatus here like this, and here's the model, and here's the real thing on the right side. Here's a picture from a publication long ago. Here on the right, I'm going to show you our original data. So what I'm measuring here is gold. Okay, that's gold, AU. And we measured this intensity as a function of momentum transfer, Q, okay? Q is equal to 4 pi over lambda sine the scattering angle, called 2 theta over 2. And when you do that, and you plot it this way, this is the pattern you get. In a traditional geometry, in a regular lab, that's all you'd be able to measure. You can't go all the way out because the wavelength is so large that at about 8, you'd be your detector would be all the way at 180 degrees. So the trick is you want to work in really high energy X-rays, because if you can work with X-rays that are, let's say, 10 times higher in energy, then you can get to these regions. Now, okay, so wait, this doesn't make yet any sense, like why we want to do this, okay? Well, I'll tell you why, okay? Because what we're going to do is we're going to measure, okay, a diffraction pattern all the way out to very high Q. And notice that the units of Q are inverse angstroms. So the neat thing is if you take a Fourier transform of that pattern, there's a little bit of processing you need, and you Fourier transform that, you know that what you're going to get is a graph that now is going to be in angstroms, and this is what you get. So what happens here on the left is you have a pattern that looks like a diffraction pattern. And this is where you remember that, like, I think it was Ashcroft and Mermin or Cattell or any solid-state textbook tells you that the Fourier transform in an face-centered cubic lattice is a body-centered cubic lattice. And this is exactly what this is. This is the Fourier transform of that scattering pattern, okay? But now what do the peaks correspond to? There's the nearest neighbor. That's at 2.4 angstroms or whatever that is telling you that that's where you're going to have a gold atom. So every gold atom will have no atoms really, really close to it, and all of a sudden it'll have a bunch. And if it's face-centered cubic, by the way, the area is going to be 12, okay? That's the number of nearest neighbors that have so the area of the curve corresponds to the number of neighbors, and the position is the distance, okay? And there's the next nearest shell, and so on. So that's how you get information about, okay, even a nanoparticle, okay? We did not need to measure the sharpness of the Bragg peaks. We just had to measure further out in Q space. So I'm going to show you very quickly some very initial work that we did, where I'm going to go very fast here because there's a lot of stuff to cover. So we first looked at some amorphous silicon, and amorphous silicon is an interesting material that, well, it's amorphous. It's not crystalline, so it has no Bragg peaks, but we Fourier transformed the pattern, okay? And we get a nearest neighbor And then the next, that's the nearest neighbor. And that's the next nearest neighbor. Okay, the next nearest neighbor, the second one. And what it tells us is that even though amorphous silicon is like this here on the right, this big mess of, oh yeah, here. So crystalline has 4 neighbors. They call 6-member rings, long range order. While amorphous silicon, which is very important for technology, okay, it has very close to 4 neighbors, but maybe not exactly. And people have a hard time being able to describe the structure. So when we did this measurement, we were able to go out to IQ and Fourier transform and get this excellent resolution. And we were able to see the nearest neighbor of silicon and show that it's very well defined, even though it's amorphous. And that's telling us that every silicon atom is really has a well-defined distance to its neighbors. And the area under the curve tells us how many neighbors it had. And by the way, the width of this peak tells you about the bond angles. So basically it's telling us, okay, this angle, let's call it gamma, okay? So this little plot here is telling us the first peak tells us that all of the silicon atoms have the same distance apart from their neighbors, and the second peak gives us the distribution of the angles between them. And so we did some, back, look at 2012, we did some ball and stick type models, and we described the pattern, and we were able to come up with distributions of angle distributions and a sort of a model of a building block of the amorphous silicon. And that's, well, as good as people could get back, whatever, 12 years ago. We also measured amorphous silicon that's been annealed and germanium that's been annealed. What does that mean? So if you produce this amorphous silicon and you heat it up just a bit, heat can be given off. And that means when heat gets given off by the sample, it means that it's going to a lower energy state, right? And so then comes this idea, and this is a whole other field of like defects in amorphous materials. And what does it mean to have an amorphous material give off heat and become maybe a better amorphous material? And how did it become better? How did it go in a lower energy state? And so here we have a picture of silicon, amorphous silicon, and germanium, okay? And a model, and this one here is a model, okay, calculation. So someone actually came up with a very nice model that matches, okay, this called a pair correlation function, okay? And it matches very much our experiments. So this is an interesting thing, and I, for you computational people out there, okay? What we did was we came up with a box. We put a box of well, computationally, we put 100,000 atoms in a box. And what we did was we calculated out, just put them randomly and move the atoms around, or calculate out the diffraction pattern that you would get from this random arrangement, and you compare it to the measured pair correlation function. And we just kept on moving atoms around and accepting moves, okay, that made the fit better. And we just kept on doing it. And we said, hey, where are these atoms going to fall? Where are they going to go? And we got this picture on the top right here. What is that? Why do I have 2 colors? Because what we found was that this arrangement of atoms gave a perfect match to the experimental pair correlation function. And what we found was, by doing a simple calculation, is that the blue ones are atoms that had 4 neighbors, and the red ones were atoms that had 3 neighbors. And there was very, very few 5 neighbors or 2 neighbors. It was very amazing. Somehow, this model had come up with a solution that really just had 3 coordinated and 4 coordinated silicon atoms. Or in this case, it was germanium. Now, we spend a lot of time thinking about this, and we said to ourselves, what are you going to say about this model? And how can we say, now we anneal it and we also fit the data? how are we going to be able to figure out what happened between the unannealed and the annealed, okay, the one that was heated and the not heated and the heated sample? The patterns change, the model moves a little bit, but how are we going to describe what's happening in this small structure change? It's just a box of 100,000 dots, right? So we came up with an idea, and this is, I don't want to take too much time on this, so pay attention, okay? What I did was I created my group did this. We created another graph here, okay? And what we did was we took, for every atom, we placed that atom at the origin of this new space, real space, you know, in meters, right? But along with it, we brought its neighbors, and we put one of its neighbors, we rotated that cluster of arrangement in such a way that its neighborhood, its neighboring atoms came along with it. We put one neighbor here on the z-axis, and we put this one on the xz plane. And these guys, or girls, they came along for the ride. And we just kept on doing that over and over and over again until we got what's sort of like I hope you're following this. This is like a statistical distribution, okay? It looks very much like probability distributions in like, orbitals in quantum mechanics, right? And we get these pictures here. So what's this picture? Well, it's not spinning or anything, so it's hard to tell. But what we have is an atom for every atom in the origin, it would have 1, 2, 3, 4 atoms around it. So our model, it doesn't seem that way, but it shows that around each silicon or germanium atom, it sits in the middle of a tetrahedron. And around each one of these corner atoms, there's like these circles. See that? And those circles actually even have, look, 1, 2, 3 more atoms. So we were able to make sense of the model on the right by remapping, okay, everything onto this other graph. And we were able to analyze, and we figured out that the 4 coordinated atoms had a local arrangement that looks like this picture on the left, while the 3 coordinated look like that. So I'm almost done with this one. What we did was we were able to figure out that the models had different motifs, let's call them, and that the very, very common 69% were these perfect tetrahedra. But the rest of the model was finding what we call buckled shapes, sort of a 3 coordinated silicon in the middle with 3 atoms hovering around it. So it wasn't really like the tetrahedron minus an atom. It was a little different than that. And what we found is when we annealed the sample, that the ratios of these 3 different arrangements changed. So we were able to figure out what happens when you anneal silicon, right? That's sort of cool. And so we had to invent ways of being able to interpret our data. Okay, now I'm going to move on to another thing. Here is our apparatus for doing these measurements. And I'm not going to spend too much time on this, but there's a picture here, and we spent a lot of time on it. Here I have a picture of a diffraction pattern. Okay, so this black thing is a detector. Okay, that detector is basically for a chest X-ray. It's designed for chest X-rays, radiography. Okay, and the X-ray beam comes along here and hits a sample and it scatters. And that's what I call the traditional geometry for diffraction. And that's this picture here on the left. But this is what we do. Okay, we put the detector at an angle. See that angle? And that distorts the pattern enormously, but it really, really improves the quality of our data. Because what happens is it amplifies the signal at really high angles or high Q, where usually you have no intensity. Now, when we first measured our patterns of some samples, this is what we got. This is not good. This is bad, okay? Not good, okay? we rotated the sample, it was in a little tube, like a 1 millimeter tube, and it's a standard sample. And as we rotated the sample, we got completely different patterns, and it was terrible. And we also saw these terrible glitches. Okay, this is terrible. This is not good. This is not good. We had to solve a lot of problems. What we realized was that the detector was part of the problem. Well, one, the sample was part of the problem. It was sort of shaking around, and I call it the washing machine effect. It's all sort of moving around. And as we rotate the tube, the sample, sometimes we had more sample in the beam, sometimes we had less. With that, we had to stop that. We had to tighten up the sample better. That was good. But the glitches were more serious and harder to solve. So we did a lot of work, and there was a lot of calculation involved. We put a detector. So here, what you see is the beam hits a sample here at the bottom. You see that? And then what we did was we put the detector on top, like a roof. Okay, and X-rays hit the detector, and our sample is this big block of carbon, and we have Compton scattering. Remember Compton? So Compton said that electrons can act like particles, and photons can act like particles, and you have the collisions. Well, that's what we're using, this cross section, Compton scattering, which is it's very important to address in our measurements. But we're using the Compton scattering to try to create a flat field on our detector to be able to correlate and figure out whether its response is uniform. So this is a picture of what we figured out. We figured out that our detector here on the right was made up of 32 panels, and each panel had a response that could vary as much as 4%. And so this was scrambling up our data. And so here we were seeing these glitches. So we figured out how, and this is important, we figured out how to correct our detector for these very important variations that were messing up the quality of our results. Now, another thing we do is our diffraction patterns are distorted like this, and we can remap them to something more useful where we call this Q. That's the momentum transfer. And here, this is just the axial, okay, or chi dimension. So it's this angular rotation, okay, from left to right. And so it's a more useful way of looking at the pattern. So we have to remap it. There's calculations involved. And so when we look at a pattern of our data, now it looks like this, like these stripes. And then we have to just integrate horizontally, and then we Fourier transform vertically. Let's keep on going. So this is what we got when we first measured our samples. We got these patterns. This is like Bragg peak. So I'm like, okay, that's supposed to look like that. But what are these glitches? That's the paneling. But once we corrected for this detector, we were able to get this, okay, pattern here, which looks so much better. No noise. I mean, a little bit of speckly noise, but very, very, very high quality data all the way out to high angles. So we have this geometry was the normal geometry that everybody else uses. This is the geometry that we're using that's enabling us to get better results than anybody else, okay? So here we published a paper where this is the intensity pattern. You see what I'm drawing? This is how the intensity is spread over a regular detector, while ours is spread in a very different pattern. So our intensity stays up high, even out to very high momentum transfer. So most people can't go beyond 20, 25 inverse angstroms. We can go out to 40. Okay, so we can get, what's that important for? Because the higher you go out in Q, the better your resolution. Okay, so this picture here, do I have another picture? This one's better. The bottom line is, and if you're zoning out, focus now. This picture on the right is what's important, okay? And that's our histogram from of a sample of nickel. And when we set up our geometry correctly, we get this blue pattern, this blue curve here, okay? And what you see is it's sharper and there's no noise, okay? There's no noise. We get really high quality data. There, that's our nickel now. So this is our nearest neighbor, okay? And we have no background. See, it's clean, okay? That's what's important. This portion here, I call the dinner, am I spelling it wrong? Fork. That's just a word I use in the lab, okay? Garfu, okay? And it's just a region that's sort of stands out when I look at a face-centered cubic structure, okay? There's this region over here. And when you're going to see, if you ever look at a publication of this sort, people will show their data, maybe of a face-centered cubic radial distribution function, and you'll see this pattern, and you'll hope you remember how clean this is, and how these peaks are going down to 0, okay, here at the bottom. It means that our resolution is very good and our noise is very small. So now we can look at nanoparticles. Hey, these are the nanoparticles that I said in the very beginning, gold nanoparticles that I said we wouldn't be able to use diffraction, and here we actually measured them, and we can see their structure. Hey, look, this is a platinum, and you can see that dinner fork that I was talking about. See that? Big, small, 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 big. It's a little distorted because it's a nanoparticle, but we can see that the nanoparticle is very small, but it's face-centered cubic. Ta-da. Just by looking at that dinner fork, okay, someone who knows what they're doing can say, oh, that's face-centered cubic. Amorphous selenium. How much time do we have? Okay, maybe that's about it. I can just tell you quickly I'm going to just show pictures. So selenium is something we did. It's a very interesting amorphous material. The big question was it made up of chains or rings? Chains or rings? I know. And we measured the sample. Very, very nice pattern. Look at the quality of the radial distribution function. And on the right here, I show our original amorphous silicon. And so very, very clean pattern of amorphous silicon. That number is 2. 2 neighbors. The area, right, is 2 nearest neighbors. And so it's a chain. And we come up with a model. And actually, this is a picture of what we see as the neighborhood around a selenium atom. So people wanted to know whether there were rings, 8-atom rings. And what we're seeing is something that maybe looks more like a chain. So you have a center atom here, and you could see its neighbors have a range of angles, and the next, and so on. But we also found there was 85% of the sample in the model came out to have this local arrangement. 12% had this arrangement. And you say, oh, is that the 8-atom ring? 1, 2, 3, 4, 5, 6, 7. No, it's not 8, and it's not closed. See, what I think is happening is that selenium actually does this. And 12% means that how many atoms, it's folding back on itself, okay? And so 12% of the atoms in the selenium are exactly where the chain folds back on itself. Isn't that cool? So even though the pattern isn't a crystal, we can say something about it. And we don't have any 8-atom chains in the model either. Last one. So we're looking at, now this is the important, my group right now is in the basement, and they're working, and we're just solving tons of nanoparticles for catalysis, for fuel cells. And here's an example of a chemist gave us these samples of palladium, and it turned out it was palladium oxide and palladium hydride. The samples weren't what they thought they were. We do X-ray diffraction, and we figured out that we had 2 different phases. It completely explains why the physical properties or the chemical properties of the nanoparticles weren't like pure palladium. And we could do the diffraction, and here's the histogram and a model, and we could do phase analysis of even nanoparticles. So that's it. And here's a list of some of, or many of the people that I work with. Thank you very much.
Okay, thank you, Stefan, for the nice presentation. Okay, now I'm going to open for questions. I think the people can ask questions also in Portuguese, yes?
Yeah, no problem.
Okay,
no,
okay, good. Okay, then if somebody has questions, don't be shy.
Sorry if I went too fast.
No, it's okay. It's perfect time, yes. No question yet? Okay, while people are thinking in questions, I have question.
Yeah, good.
Using the system that this equipment at the high energy, also it's possible to measure, for example, organic amorphous material also, or this is more dedicated to metals, because you show more metals.
You're right. Okay, the method is, look at what I'm looking at, polyethylene.
Polyethylene.
Okay, it's
nice.
very difficult, very difficult to look at light elements. Okay, and what's a very interesting thing that happened when we put our detector at this funny angle, and we addressed all of these issues that we did. We improved. We had to use parallel processing with GPU. 10,000 core cards. My group does a lot of computational calculations on the data, and so they're all becoming experts at this.
Good.
But we figured out how to get our detector to work well, and we come up with these big models. But what's happened because of that is we are now able to analyze samples that are like organic, okay, and so like hydrocarbon type structures. We look at things like nanocarbon, nanodiamond, all sorts of organic stuff. And it turns out it's very difficult because here, this is like, what happens is, this isn't showing it, but when we measure this blue pattern, that's the elastic part that's giving us the data, that the structural information, but there's also this Compton. And the lighter elements have more Compton. And so it's like 99% Compton. And you have to eliminate that properly. It's very difficult. And so people usually can't do it. Okay, they can only go out to here because it's only where your elastic scattering is comparable to Compton. Out here, you have a lot of problem. But we were doing it, and we're able to get really nice patterns of, that's a pair distribution or radial distribution function of high density polyethylene, and that is also it's like a chain like this, where you have carbons, and then each carbon has like two little hydrogens. Okay, and that's the picture, and it's working out. Okay, so here's a picture of this is a neat picture of the one of my undergraduate students was doing a calculation, and the blue is what happens, the carbon distance. Okay, 1, 2, 3, 4, 5. It's like I call it a hegwa, a ruler.
Okay,
right?
ruler.
And it just keeps on going, and you can see that in the data. It's all there, so you can see all of the correlations. And you know what? By looking at those blue peaks, if the chain was doing something like that, going in a curve, you would see the distances shifting to smaller angles, wouldn't you? So you should be able to tell whether the chains are straight or curved.
Okay.
By doing an analysis of this. So it goes back to my meter stick analysis. But also, it's complicated. There's an amorphous component. We're finding a lot of subtleties. Okay. Here's okay. So we can figure out the vibrations of the atoms, and everything. And so yeah.
Okay. It's a nice technique to let's say corroborate with the neutron scattering in elastic scattering, yeah, because you can even see vibration, and also you can use X-ray at high energy to see these small details. Yes.
The comparison between X-rays and neutrons is really excellent. Okay. And one of the things that we can see are the electrons. So neutrons don't see the bonding, but we get affected by bonding.
Yes.
Okay. And so we can see bonding when the neutrons don't. And so if we actually measured both, and you looked at the difference, you could see what was the difference between atoms and bonds. Pretty neat, right? Like, let's just imagine in this picture. What happened here? That could be what happened here? Right. That could here, for example, why is that blinking out? 1 second.
Okay.
The somehow I think the program is telling me it's over. 1 second.
Okay.
So if we had bonding, for example, between atoms, it would look like that. You're seeing the picture, right?
Yes, this picture.
Okay, so what I have in that circle, that could be bonding of, like, let's say, electrons between two carbons. Neutrons wouldn't see it, but X-rays would.
Okay.
So that's really neat.
Yes,
right?
it's really interesting. Yes.
You can imagine if a sample was going through phase transitions, maybe we would see the electrons doing things, the electrons between the atoms doing things. Neutrons wouldn't be able to see that. We would. So with the neutrons, we would rule out, right, that these things aren't between the atoms, that it really is the bonding. And then we would be able to explain, like, imagine if these bumps in between the main peaks were bonding. Okay. Yeah.
Okay,
Anyways,
well, that's very interesting. Yes.
Okay.
So,
yeah. That's. Any questions?
Yes.
Come
more
on.
questions? Não fiquem tímidos, porque pode fazer em português.
Então, eu vou perguntar. Alguém tem uma pergunta? Qualquer coisa. Muito bom.
Quem que está falando? Pedro.
Sim. Sim. Ok. Boa pergunta. Então, o que acontece? Vamos ver se eu posso achar espaço e se essa coisa vai deixar. Ok? Ok, essa é importante. Tem 3 diferentes formulários. Vamos ver se eu posso. Ok? PDF, RDF e PCF, ok? Quando você começa estudando essa área, ok? Às vezes fica confuso, uma pessoa fica confuso, porque diferentes cientistas gostam de falar sobre pair distribution function, radial distribution function, and pair correlation function. Eles são diferentes, ok? E não é só uma outra palavra para a mesma coisa, ok? Ok? O radial distribution, na minha opinião, é o mais fácil para entender, ok? Esse aqui, em verdade, é o histogram. Ok? Histogram nós não usamos muito em física, mas talvez pessoas em economia, alguma coisa, usam mais. Hein? Mas o histogram vai ser, ok, o número de vizinhos que você tem em um círculo de radius r, sim? Então, você faz por cada átomo dentro da estrutura, você vai fazer um círculo e você vai ver quantos vizinhos você tem no esse círculo. E quando esse círculo fica maior e maior, a superfície fica maior e maior, e essa vai crescer como R squared, ok? Então, o radial distribution function sempre vai querer crescer, ok? Igual R squared, ok? Quadrado. Ok? Num círculo, um sphere, ok? Vai crescer assim, ok? Então, essa se chama RDF, ok? Se você tinha um material que não tinha átomos, parece completamente isotropic, ok? Uniform isotropic, como sempre você estuda em electricity magnetism, assim. Então, o density ia ser simplesmente uma curva assim. E essas diferenças que estamos vendo são a diferença porque você tem átomos, ok? Aqui, essa se chama PDF. E PDF é inferior, na minha opinião, ok? Porque esse aqui não tem sentido como histogram, ok? É uma manipulação de matemática que tira esse R squared, ok? E coloca tudo numa linha. Agora você sempre vai ter uma linha assim, que é por causa da densidade, mas essa aqui sempre vai continuar, ok? Indo em volta do zero. Agora, pair correlation function é um que fica parecido. E as pessoas trabalhando com neutrons gostam desse aqui. E parece, não pair distribution function, mas você tem o seu primeiro vizinho e depois você tem estrutura que vai em volta de 1 em vez de 0. Ok? Então, tem 3 diferentes jeitos para mostrar os dados. Eu tinha outro pair correlation function. Ok? Mas boa pergunta. Vamos ver. E você viu, por exemplo, quando você tem um nanopartículo, porque o partículo tem um tamanho, vamos falar 2 nanômetros, o máximo distância que você vai ter entre 2 átomos vai ser 2, ou 20 angstroms. E essa razão que essa curva não continua crescendo é porque todos os átomos são dentro de um volume pequeno. Você viu? Você viu? Essa ia ficar assim, mas o cristal não é tão grande. Ok? Bom. Bom, boa pergunta.
Nossa, bem interessante. Eu pensava só do pair distribution function, mas agora você falou dos outros, é bem interessante. Mais alguma pergunta? Or questions? Eu acho que já... bom, quase já está na hora, né? Já passou das 5 horas.
Okay.
Bom, Stephanie, can I give you... I give them your email if they want to contact you, or yes, be very nice. I have just one small question, maybe you can answer about to apply for your beam line. How difficult it is, or what we need to do? There is the same process as we do here in Brazil, or
hey, one more thing. Eu não sei se vocês querem, mas uma pessoa pode virar membro do Canadian Institute of Signal Radiation. Custa $25 canadense, eu acho, sim. É $25 canadense para cada 2 anos, ok? Então, é $12. E canadense é bem mais fraco do que
o dólar,
o dólar americano, ok? Mas, ok. Mas, não, se uma pessoa quer saber mais sobre o síncrotron de Canadá e como está crescendo, tudo bom. Mas... agora, para fazer propostas, você precisa olhar no CLS, procura no internet CLS website e precisa procurar na página, e você precisa montar uma proposta, ok? As pessoas, ok? Tem 2 jeitos, ok? Um é para escrever uma proposta, outra Comunica comigo e talvez eu possa
perfeito.
direcionar alguém, talvez para um colaborador que trabalha nessa área, se vocês querem trabalhar com um canadense que trabalha numa área ou outra, sim, eu posso fazer alguma coisa. Agora o síncrotron canadense está fazendo um upgrade, ok? Está melhorando. E vai ficar fechado até talvez dezembro, ok? Mas depois vai começar de novo. Então, dá tempo para escrever propostas, ok?
Isso.
Ok? E as propostas não são tão compridas ou nada.
2 páginas, talvez, né?
É pequena, sim. É igual do síncrotron brasileiro, eu acho.
Ok.
Mas você vai ver, as linhas são diferentes, ok? Nós não temos o mesmo tipo de síncrotron de 4 geração. Então, mas tem 40 estações de trabalho, ok? Tem muito diferente para fazer imagem ou espectroscopia de várias diferentes energias. Sim.
E dá para aplicar no seu instrumento também, né? Na sua linha, né?
Claro.
Ok. Então eu vou fazer isso.
Bem-vindo, por favor.
Legal. Ok. Perfeito.
Sim.
Então tá certo.
Okay.
Então,
sim.
ótimo. Então, ok, vou falar em português, né? Porque
sim, claro,
você fala muito bem português. Então, novamente agradeço, professor Stefan, por ter aceitado a dar uma palestra aqui para o grupo, né? Para pós-graduação aqui de Física da Universidade Federal do Paraná. E se as pessoas quiserem entrar em contato com você, eu posso daí mandar o seu contato, né?
Sim.
Então, mas novamente, muito obrigado por ter feito uma palestra muito interessante, assim, trazer técnicas novas, né? Que a gente sempre trabalha com raio-x ou neutros, a gente sempre vê a parte de difração, espalhamento baixo ângulo, mas assim, mostrando que então dá para tem ainda muito que ser desenvolvido em raio-x, né? Para se ver mais detalhes, né? Nos materiais. Então,
e nós temos linhas de sax também.
Legal. Tá.
Sim, temos. Temos uma linha no nossa Brockhouse Sector que faz sax. Então,
isso é bom saber.
E só começou, não tem tantos usuários ainda.
Ok.
Então, e as medidas são rápidas. Sim.
Ok.
Escreve uma proposta para sax.
Então, vamos escrever propostas para sax.
Muito bom.
Então, tá bom.
Okay.
Mas, novamente, muito obrigado, Stefan, por ter dado essa excelente palestra, e a gente vai entrando em contato. E, assim, eu vou passar, então, né, se os alunos tiverem interesse em entrar em contato com você, seu contato para futuras colaborações.
Sim. Tudo bom.
Então, tá certo.
Ok.
Então, mas muito obrigado. Então,
ok.
Então, tá bom. Então, obrigado a todos, e aí a gente vai se comunicando.